Hello, Honors Trig and Pre-Calc. I would like to start this video just by saying that this is the first video I am doing from home with a tablet I have, and it's not super easy to use, so please forgive me if my writing is not so good. We are just going to have to make do. Also, this video is going to be relatively short. It's just going to be talking about the general topics here. I will possibly make an additional video with some practice problems if I have time. Otherwise, please reach out and let me know if you want specific problems based around these topics. All right, let's get to it. So this is our limits and continuity review, just general review of all this limit business we have been doing during this time. So the first question is, what is a limit? And the easiest way, or maybe not easiest, but best way I'm going to define a limit is it is going to, oh goodness, tell us what our y value is approaching as, oops, that's supposed to be an S, as x gets close to some value. All right, that is really what a limit is. It's not necessarily the kind of important thing here. It is not telling us what y actually is. Again, we are looking at what y is approaching, what y is getting close to. Notation for our limits, we're going to say something like limit as x approaches 3 of this function is equal to, I don't know, let's say 7. That would be something, let's say, that looks like this, where this is x equals 3, and I'm going to change the color, and that would be 7. This is not a very interesting function, but oh goodness. But an example nonetheless. All right, so there's a couple different things that we talked about in this section, and they are about evaluating. The first was evaluating graphically, which I kind of just showed you in this picture here. Really, the best way to do this is to look at what the y value is approaching as x gets close to something. One hint would be to when you are looking at a function like this, to literally take your pen and follow the function. So let's say I have something that looks like this. Let's go with 1. We'll say this is also 1, and this is 2. The other piece that I have not touched on yet is when we're talking about limits from just the left and the right. So here, the limit as x approaches 1 from the positive direction of this function, positive direction meaning coming from the positives, this would be equal to 2. That's what the y value is. However, the limit as x approaches 1 from the negative side of this function, we look from the left side, from the negative, would be in this case 1. And then the last piece here, we've got, oh goodness, what did I just do? We've got limit from the left, limit from the right, but the final question is, what about the limit at 1 period? So the limit as x approaches 1 of this function, well, look, as it comes from the right, it's at 2. As it comes from the left, it's at 1. If those are the same, it would be whatever that number is, but because in this case they are different, the limit here does not exist. Why? We've got to jump. All right, I paused the video, made that smaller. The second thing we talked about was algebraically evaluating limits, and remember there's a general step-by-step process here. Step 1 is always going to be to plug in whatever that value is. Oh. Ah. All right, sorry, technical difficulties. Plug in the value and evaluate. If you get a number, you are done. If you get 0, you're done. If you get a number divided by 0, you're done. But the thing we need to look out for is that 0 over 0 case. When we had this, we know we need to do more work. What does that more work mean? Typically, our more work is going to be related to factoring, or to get rid of a radical in the denominator to multiply by a complex conjugate. Sometimes the quote-unquote more work was really just simplifying the equation that you had, but in general, we can do those two things when we notice that issue with the 0 over 0. All right, this next slide is going to be super fast. There is the special kind of limits. There's a couple sections here we've got. The first is about our trig limits, and these were those 3 equations that I said you just kind of have to know. If you ever see the limit as x approaches 0 of sine x over x, that will be equal to 1. Similarly, if you ever see the limit as x approaches 0 of tangent x over x, that limit is also 1. And last but not least, the limit as x approaches 0 of 1 minus cosine of x all over x is equal to 1. These are the 3 that I would expect you to know. Make sure they're clear on your notes sheet so that you can use them at any time. If it is something else, like the limit as x approaches pi over 2 of tangent of x, that we're just going to do like we were talking about before algebraically, plug in the value and simply evaluate. Next up, we have limits at infinity. So this is something where we have a function and we have some numerator function and denominator function. I am going to say the degree of our numerator is a, and the degree of our denominator is b. I cannot remember what variables we used last time, so I apologize if I'm changing them on you right now. And our limits at infinity looked at comparing these degrees. So there's 3 possibilities that could happen. A could be less than b. Option 2 would be a is equal to b. And option 3 would be that a is greater than b. In the case where a is less than b, this would be like our good old 1 over x, which hopefully you remember what that graph looks like, and the limit as x approaches either positive or negative infinity, in this case for this function or any function where a is less than b, is going to be 0. Why is that? Again, that's because of our horizontal asymptote at x equals 0. Second option would be when the numerator and denominator have the same degree, or a is equal to b. In this case, your limit, oh, I do not want it to look like that. Hold on. All right, sorry. In this case, your limit will be equal to the leading coefficient of your numerator divided by the leading coefficient of your denominator. So it's going to be a number. Why? Again, this has to do with our horizontal asymptotes. And so this one is just going to be a number, and it's fairly straightforward. Last but not least, we have the case where a is greater than b, and this one is maybe the most challenging, but honestly it's not that bad, I promise. In this case, to find your limit, you are going to quote-unquote do the division. Now, you don't actually have to do any division, but what I mean by that is you're going to take the leading coefficient, the entire thing, of the numerator and divide it by the leading coefficient of the denominator. And whatever function you are left with, you are going to take this function right here and consider the leading coefficient test, or the, that's not what it's called, but I can't think of it right at this moment. Leading coefficient test. So that thing that we do with polynomials, for example, let's say we had 4x to the 7th. For this function here, we have an odd degree, but we have a positive coefficient, which means I am going to have something of this form for my, end behavior is what the words I was looking for up here. End behavior here. So if I am looking in function, the limit as x approaches positive infinity of this function, and this was my value over in this little circle over here. As x approaches positive infinity, what's happening to my y? It is approaching positive infinity. Therefore, technically, it does not exist. And if we did the limit as x approaches negative infinity of this function, as it approaches negative infinity, my y is also approaching negative infinity, therefore does not exist. Last thing in this section was continuity, and the first thing I want to talk about is continuity at a point, what it means to be continuous at a certain point. So there's three things that must be true in order for a function to say, yes, I am continuous at this point. First thing is that the limit must exist at that point. The second thing is that the point must exist. And third, and maybe most importantly, the limit must be equal to the point. If all three of these things occur, then that means that the function is continuous at that point. I'm going to draw a couple examples here, though, to kind of show you what I mean in a lot of different cases. And we will see what happens. So let's say I have a function that looks like this. There's a hole. This is point A. In this first case here, the limit exists at A, meaning on the left it's the same as on the right, so the limit exists, yay! But there is no point. The point does not exist. So is this function continuous at point A? We would say no, not continuous. Let's draw another one. What if our function looks like this? Here at A, the point exists. We have a completed point, yes, but unfortunately, the limit does not exist. Why does the limit not exist? It is different from the left and from the right. So is this function continuous at A? No. What about a function that looks like this? Here is A. In this example, the limit exists. Look, it's right here, whatever this y value is. Okay, so the limit exists, yay. The point exists, hey, look, it's up here. But here's the issue. The point is not equal to the limit. So is this continuous? No. In order for a function to be considered continuous at a point, all three of those things must happen. It must be continuous, meaning the limit exists from the left and from the right, the point actually exists, and the limit is equal to the point. This is an example of continuous at point A. Last little thing in this section was different types of discontinuities or breaks in the graph. We have three main types. We have jump, we have essential, which can be two kinds. We have infinite, or our vertical asymptotes, and oscillating, which I've shown you pictures of, but you would probably not be expected to know what that looks like just from the graph. And then last but not least, we have removable, which would be our holes. This third one is kind of important because we can plug the hole or fix a removable discontinuity. How did we do this? Well, these were the types of problems where it said extend the definition. Oops, that was really bad. Extend the definition. And basically what we did is we took the limit to see what should our y value actually be at that point, and whatever our limit is would be the actual value we would want in that definition. I'll probably do an example of this one later, but I don't want this video to be too long. So that, in a nutshell, is what we need to know for limits and continuity. Have a lovely day.